Hello, and welcome back to our Calculus 1 course. Today we're talking about continuity. Up until this point, we've talked a lot about limits. We've talked about our left and right-handed limits and how we need them both to equal the same value in order for our entire limit to exist. We've talked about the different limit properties that we have, which allow us to actually manipulate our limits and rewrite them into a way that makes it easier for us to solve them. And we've talked about a bunch of different techniques into actually solving limits and to be able to compute what these limits will actually equal. We've talked about our infinite limits and our limits at infinity, which, as their name implies, involves infinity. So with our infinite limits, they'll equal a positive or negative infinity, where the limit does not exist, but they are a special case of does not exist. We have our limits at infinity, where we have our limits where x approaches positive or negative infinity, and these can equal actual values. And these limits do exist, and these are often used to find horizontal asymptotes. Today, we're talking about how we can actually use limits. So instead of actually going through ways of solving limits or computing limits like we have been doing in the past, today we're actually going to take a look at how we can use limits in a broader sense into our mathematical ability and how we can actually use them to prove things that we haven't been able to do so this far. Today we're talking about continuity, and continuity is something that you kind of just have an instinct for since the time that you've been able to start writing. Something that you can actually tell without looking into the weeds of all of the math and the definitions that go behind it. So a function is continuous, then there are no breaks in the graph. And this is what we're saying, is that you can trace the graph with your pencil without lifting off of the page. And so if I look at this graph in the bottom left, I can trace along this whole graph, and I didn't have to lift up my pencil. This function is continuous, and you can feel it intuitively because I didn't have to move my pencil off of the page. I can just continuously draw this line. And we have our mathematical reasons for it. A function f of x is continuous at x is equal to a if f of a is defined. So for our first rule here, if we have a graph, this graph is discontinuous at a because f of a does not exist. It is not defined. There's a hole right here. A doesn't equal anything. And so as I trace along this graph, I have to lift my pencil up at this point because it doesn't exist. Our second one is that the limit of f of x exists. And so in our second graph here, this limit does not exist. I have a left-handed limit and I have a right-handed limit, but since they don't agree, the limit does not exist. However, f of a is defined. It does exist. It equals this point up in the first quadrant. So f of a is defined, but the limit, the total limit, does not exist. And you can see that this is not continuous. I have to lift up my pencil in order to draw the rest of the graph. And finally, the limit as x approaches a of f of x must equal f of a. F of a is defined, so we have this point down here. Our limit exists because I can trace from the left-handed side and the right-handed side, and those equal the same point. So our limit does exist, but our limit does not equal our f of a value. And so if I'm trying to draw this graph, I have to lift my pencil up, draw this dot down here, and then go back and draw the rest of the graph. There's no way that I can draw this whole graph without lifting up my pencil because I have to make this discontinuity here. Back to our first graph, we can see that this is continuous at a and the entire graph because a does exist at this point. The limit exists. I can trace from the left and the right-hand side, and they equal this point here. And so our graph is continuous at this point because all three of these rules are true. You can also have one-sided continuity. So if we take a look again at our second graph, we have this graph here where if we take our left-handed limit, that does not exist at a because we have this open circle. However, our right-handed limit, we do get a point here. So this right-handed limit does exist. And so we can say that f of x is continuous from the right at a because I'm looking just on this point of the graph at a. And so one-sided continuity is if you're looking at a particular range. So here I'm looking at, okay, is this graph continuous up until the point at A? And it is. It's only continuous from the right because this point is closed. This graph is not continuous from the left because we have an open circle. Now if we're looking at discontinuity, we have 4 different types of discontinuity. Our first one is removable discontinuity, which is where we have a hole. So we can have these 2 sides, but I have to lift my pencil up because of this hole. And you can have a point that has been removed and moved out of place, but you don't need to. So these are removable discontinuities. You can have jump discontinuities where the graph will continue, but you still have to jump and move out of the way to a different spot in order to continue drawing the graph. You can have infinite discontinuities, which is here where you have an infinite limit on either side and you have a vertical asymptote. And finally, we have our oscillating discontinuities, which is what we saw with our squeeze theorem. So on these graphs, you have something that's oscillating up and down, and as you get towards the middle, the function does not exist. So you can't find f of a. It does not exist at that point, and so you can't find the limit equaling f of a. And you can feel this if you were to trace the graph. You would have to be tracing this graph for forever as you get closer and closer to 0 because of the oscillating nature of the graph. So that's all I've got for continuity. It was a quick video, but I will see you in the next one.